Hello all, and welcome to the last and most exciting day at the Wireless Village. My name's Zero, and on behalf of the Wireless Village team, I'm very happy to introduce Adrian Chad. Adrian came up to us during our training class at B-Sides Las Vegas and said, "Oh, hi guys. I worked on the Atheros HAL code, and it's my fault that it's all open source now." He's a BSD developer, but we're not going to hold that against him for right now. So, without further ado, I'm going to introduce the man who said, "If I wanted to, I could win your CTF, but I don't want to."
It's true. Hi, I'm Adrian. As a brief introduction, I worked at Atheros at about the time they got bought by Qualcomm, so I got to experience both the happy side of it and the not so happy side of it. So before we begin, I'm one of the dirty bastards who signed the NDA to get access to all the shiny toys. So everything that I'm about to tell you, you can actually figure out for yourself. I'm not going to tell you anything that you shouldn't be able to figure out by reading the available source code and all of their patent filings. And if you really want to dig into it, there's a bunch of IEEE presentations from the silicon people talking about the interesting crap they do in silicon. And I really hate writing slides, and I really hate drawing diagrams, and all the diagrams I have are under NDA. So I suggest if you're actually interested in a picture representation of how the chip looks, do some Google searches of your own. I went and did some Google searches, and there's some stuff out there, but they're in leaked data sheets. And for obvious reasons, I'm not going to post linked data sheets on a recorded talk. But it's all out there. So, the Atheros hardware. The first thing that people think is going on inside it is that there's a CPU doing all the cool shit. And back in the day of the Prism and Prism 2 chips, there actually is a DSP in them that's actually doing a large part of the Mac and PHY related activity for the DSSS and the CCK encoding and decoding. However, there is no CPU in the core in the Atheros chips. By design, they put everything into silicon, and anything that would run in a CPU, they punt to the host operating system driver, which gives us all the shiny toys that we have. So the bits that are interesting is the Mac, which implements all the 802.11 data level bits, like generating frames, doing ACK, doing RTS, CTS, contention, back off, all the timer-related stuff. And you can see this as a great big DMA engine with thousands of little timers implementing 802.11. There's the PHY that does all of the actual physical layer encoding. So that's doing CCK, OFDM encoding and decoding. It has multiple spatial streams for 11N stuff. And there's the radio that does all the actual RF bits. And so the PHY takes in and out like a 20, 40, or 80 megahertz wide baseband signal, and the radio is the thing that steps it up and down to 2 and 5 gig. The real-time clock is clocking and also power control, so that's the bit of the chip that's bringing everything to, bringing power on and off and handling clock generation. And then there's the host interface, which is the PCI, PCIe, the SDIO, inside the little tiny SoCs that you can get all those little TP-Link and D-Link access points. They'll have a single chip Atheros MIPS CPU with a Wi-Fi chip on board, and the chip internal to the Atheros SoC is actually connected via a standardized industry protocol called AHB, which means something that I don't remember. Okay, so the Mac consists of some bits that do DMA. So in Atheros terms, the PCU handles the receive DMA, and the DCU handles TXDMA. The Q control unit handles implementing all of the 802.11 crap. So if you want to fiddle with timing, I'll explain that in a minute. The QCU is the thing that you program to modify how 802.11 behavior works, and the DCU is the bit that just takes packets in and DMAs them into the TX-FIFO and sends them out. All of the stuff that's time sensitive gets handled by the Mac. So ACK generation, for example, can be done in hardware. There are timers to program how long it'll wait for an ACK on the receive side, and you can disable sending ACK if you really want to, and you can disable expecting an ACK as well. RTS and CTS, AMPDU for 802.11n, block ACK, all of that crap is time sensitive. There's no point doing it in CPU. If your CPU's interrupt handler, it takes too long, then you'd miss your ACK window, and crap would be silly. So all of the time sensitive bits are done in hardware and nothing more. The PHY handles all of the bits that actually do 802.11 data. So it handles stuff that goes over the air. So it does the clear channel detection to figure out when it's time, when it can transmit. It does signal detection and signal sizing, antenna selection, all the encoding and decoding. It handles all the MIMO stuff. The important thing here is there's one massive PHY in the 11N chips, and for each physical radio, there's one set of FFTs and IFFTs going on, and then it funnels all of that crap into one ginormous PHY that's doing all of the signal correlation and processing in silicon inside the PHY, and it's kind of scary to look at. The radio handles all the RF synthesis, and there's some back chat between the PHY and the radio that I can't talk about, but most of that's to do with automatic gain control and signal sizing. So every time that you receive a packet, the first thing the receiver needs to do is figure out how to size the packet, to size the signal so that it fills the dynamic range of the ADC, but it doesn't saturate it to the point of distorting and screw up receiving it. So there's a lot of fine and coarse grain automatic gain control going on per packet and per antenna as well on the earlier chips. There's some filtering going on, and I'll talk about that later. In the earlier chips, if you've ever popped off the metal shield, there'll be two chips. And the first one is like the AR5212, which implements everything except the radio, and then they put the radio in an external part. So you have a 2 gig part and a 5 gig part, and then a 2 and a 5 gig part. And the really early stuff actually generated 2 gig first, and then upscaled 2 gig to 5 gig in a separate part. And all of that's gone away now. So with improvements with figuring out how to do analog crap inside the same chip, they have one die that has either one or more bits of silicon inside the packaging that does all of the stuff, including baseband synthesis and RF. So anything that's 11N after the AR9160 is all one chip. And that leads to quite a lot better sensitivity. So just as a side note, the chips get more sensitive on the receive side the further up the chain you go. So I do my wireless sniffing with AR9280 and AR9380. They have ridiculously sensitive receive sides. And the only thing that the PHY and the radio communicator AGC updates, you can program the radio directly, but you only do that to configure the synth. You don't actually touch it after that. And the RTC handles all the crap dealing with clock generation and... What the hell just happened there? Tech support. Swipe. Yeah. So the RTC handles only clock generation. So that handles if it's in 5 meg, 10 meg. Keep going, yeah. The chips can do 5 meg, 10 meg, 20 meg, 40 meg channels. And so one of the parts of figuring out how to do that is they actually clock the chip at a different rate. And that can happen dynamically as well when you're doing 20 meg to 40 meg dynamic packet stuff in 11N. So the only thing that you can program when you put the chip to sleep is the RTC, and the only thing you can tell the RTC to do is wake up the chip. And so when you're actually a laptop doing power save and you want to put the chip to sleep and have the chip wake up when the access point says there's something for it, this is the thing you're fiddling with. And the host interface glues all that crap together. So it's probably not interesting for most of the stuff that people are doing with these things, but a lot of the bugs that pop up is because there's issues with the PCIe power save on the chip and the laptop getting out of whack and causing the device to go away. So the Mac in detail, there's no one uses anything before the AR5212 these days, and so I'm not going to worry about the early stuff. But the new stuff has 10 transmit queues and 1 receive queue, and the newer stuff has 2 receive queues. They're implemented as in a priority scheme, so the lowest transmit queue has the lowest priority and gets preempted by successively higher queues. Q9 is always for multicast traffic that happens after beaconing, and Q10 is always the beacon queue, and you can't change that. And as I said before, they're split into 2 halves. There's the control unit and the Q control unit and the data control unit. The QCU handles all the stuff that has to do with timing and 802.11. So if you're doing things like wanting to have long transmit bursts, you program the QCU, and that handles starting, gating the DMA to start, doing the 802.11 stuff to say, I want to start transmitting programming the nav in the air to reserve the airtime so you can actually do an 802.11 QoS transmit burst. That's all done by the QCU. And the DCU is just gated and doing DMA. And the receive side is pretty simple. You program in where you want DMA descriptors to, and it just happily DMAs received packets in. The thing I haven't mentioned here that I should is that there's a filter for filtering out packets. And this is one of the first things that gets interesting for what you guys are doing with this stuff, because the filter bits let you do interesting things like, give me only stuff for my associated station, but you can also just say, give me everything, which is actually kind of useful, especially with what you guys are doing. You can also say, give me everything including management traffic, which means you see RTS and CTS and ACK frames, which you wouldn't normally see because that sort of stuff is not data related. But if you're doing like driver development like me or spoofing crap like you guys, you may want to actually see RTS, CTS. You may want to generate ACK frames, see ACK frames come in. On the later chips, they have a high priority queue and a low priority queue. Not very interesting for most people. The reason the high priority queue exists is so that low latency frames like power save data frames can preempt like having a large backlog of bulk received data frames coming in another queue. So unless you're riding a station driver, it's probably not that important. So the PHY is where things get a little bit more interesting. Because it's all done in hardware, and once the chip ships, they can't change it. There's like 1,000 registers in the damn thing, and some of them are per radio. So you end up being able to tune pretty much every piece of behavior of the PHY. And as they figure out that there's more weird shit going on in the real world, they'll add more registers to give you the ability to twiddle things so that when they deliver the chip and they find that stuff in the real world starts acting nasty, they can actually modify the PHY behavior by shipping a driver update. So the interesting things for people wanting to screw with Wi-Fi is being able to do things like override signal levels. So when people who are doing long-distance links, they're always going to hear weak signals. And they may want to have fine-grained control over making the AGC sensitive to far-away, low-level packets. But if you're in an environment like this, you may only want to receive packets that are close by and not spend time trying to figure out if the packet is far away. So you can program that and the chip will actually implement gain control based on stepping sizes and timing. CCA is something I keep being asked how you disable, so you can just transmit whenever the hell you want. There's a register. If you read the driver, you'll figure out which register you program to have it disable clear channel, but I'm not going to tell you how to do it. But you can actually set the CCA threshold for exactly what level it should be considering the air that's busy. And that has actually changed over time, so it is configurable. You can do per packet transmit power, so you can actually set the card to transmit at a high power, but for things that are close by, you can actually lower the transmit power per packet, so you can do things like confuse people doing Wi-Fi positioning, because they're typically doing, if you're doing it using open source tools, they'll be doing it using signal strength, and if someone's screwing with their transmit power, all of that stuff breaks down. The interesting things, if you're looking to twiddle with a lot of this stuff, is looking at the calibration and the noise immunity code. If you read the patents on those and the code, you'll actually get a pretty good description of how the Atheros PHY works. Because all the pre-Qualcomm patents cover the PHY design in quite good detail. So I recommend anyone that's interested to read that. And the RF synth is the final bit here. It does, well, the RF bits. The stuff pre-Merlin or pre-AR9280, you don't get to pick which frequencies you tune to. You only get to tune to what are pretty much the 802.11 channel offsets. The later stuff, so AR9280 and later, let you tune to like very, very small fractional increments. The thing to keep in mind is, and I'll cover this soon, is just because you can tune to those frequencies doesn't mean that you can actually use them. It also has a configurable width filter for both receive and transmit. So on the receive side, it filters out crap from adjacent channels. And on the transmit side, it actually prevents the transmitter from spearing crap outside the configured channel width. And when you're trying to do half and quarter rate stuff for really long distance links, this stuff is actually pretty important. So now we get to the why do people like these things? And in short, everything inside is exposed. And because they needed to make it so that they could ship software driver updates to modify behavior, the chip pretty much lets you get away with bloody murder. So the only thing that happens is the stuff that offloading would be a pain in the ass. So you pretty much get the raw 802.11 frames going in and out of the device. There's no DSP, there's no CPU in the non-mobile products, so everything has to be done locally. So on the transmit side, you do give it a raw 802.11 frame. Everything from the source address, the source MAC address onwards gets dumped into memory, and that will just appear on the air. The chip doesn't care what you put into it. The only thing you have to worry about is some magic alignment constraints. But you could pick a random MAC address to transmit from, and it will dutifully send that. So this is why these things are good for injection, because they're not enforcing any kind of source address verification inside the chip. So if you screw up, then you're screwed. But if you want to specifically spoof other things, you can. And people have used this for all kinds of interesting things. One common thing that people don't do when they want to be a naughty device is they won't disable ACK generation. So if I want to go out and see if there are anything nasty out there, I can actually send probe requests to station MAC addresses, and the hardware will ACK it for you. And you won't know because you're just simply a driver, and the driver doesn't handle ACKs. You can turn off ACKing in the chip. So if someone tries sending you a packet, even if the driver tosses it later, you still don't want to necessarily ACK to the packet and tell someone you're there. You can also disable FCS checks, so you don't have to, to the receive side thing, it's no big deal. And you get to do things like per packet transmit control. Interesting, okay. On the receive side, you get everything. So it's all based on what you get with what you configure in the filter. But if you turn on the promiscuous and the promiscuous management bits in the driver, you get every frame. And if you disable FCS checks, it'll give you every frame, including all the errors in the frame. And there have been research papers that actually look at what kinds of bit errors occur in packets, and they all use Atheros stuff, because it's the only chips you get that let you do this kind of tricky shit. So what other things can the chips do that are interesting? So I'm going to gloss over them because I only have like 30 minutes to talk about this stuff. And there are a lot of other stuff that if you want to find out, come and see me. But the chips have to be both a station chip and an access point chip. And later chips want to be a station chip and an access point chip and do ad hoc for P2P Wi-Fi direct stuff. So in order for all of that crap to exist, there has to be support in the chip for things like tracking multiple TSF counters. So if you're trying to do ad hoc and Wi-Fi and station, you need to have one TSF counter synced to the access point and a second one running your ad hoc network. The more interesting stuff for people doing naughty things is things like the AR9280 spectrum analysis mode, where you can actually get the chip to give you per OFDM bin power readings. And so a lot of the enterprise products will actually have a NIC in there specifically to pull out the spectrum data from the current channel, so they can make decisions about how dirty the channel is. If you're doing it based on RSSI only, you're only getting an idea of how much Wi-Fi traffic there is on a particular channel. But if you use the spectrum node, you can see things like microwaves and cordless phones and other kinds of noise generation devices that the chip will treat as noise but won't give you a receive packet for anything. So I use this for a lot of debugging, and it's good to see things like microwaves in action. And the later chips actually have Wi-Fi positioning hacks, so you can do fine-grained packet timestamping and actually do time delay between transmitting a packet and getting the ACK back, so you can actually estimate distance down to a few feet. And that's the kind of crap that powers your enterprise APs tracking you walking around. That's all in these things. Now, the things that you're not supposed to do, and I'm not going to tell you how, they're required as for regulatory compliance. So you're all pretty spoiled. You buy a laptop and it works, and you don't necessarily see the crap that goes on behind the scenes. And what goes on behind the scenes is submitting it to the FCC and getting the thing verified that it's actually behaving correctly or correctly. So one of the things that happens is you need to be able to verify that your chip is transmitting on a particular center frequency and not drifting over time. Otherwise, it's not going to interoperate well with other devices. So you can actually put the chip into a just blurst crap out mode but just blurst out a tone. Now, if you did this in the real world, the Wi-Fi in your area shuts down. It's actually kind of pretty to watch. The minute you transmit a carrier tone at maximum frequency, you don't care about distortion, no one else's Wi-Fi works. Don't do it. I'm just telling you, don't do it. What you do is your own problem, but don't do it. You need to know how to do these if you're submitting your equipment for FCC testing. And I'm pretty sure most of the crap that we buy, where they just take an Atheros NIC and they shove it into an existing design, like a board, and they make it work, that's not actually being FCC tested. Getting something FCC tested isn't getting an FCC tested NIC. It's actually getting the enclosure and the antenna tested as part of a product. So they end up having to implement this stuff and then prove it. The other interesting thing is you actually get to put the NIC into debug modes where you get to inject and receive raw ADC data. And it's useful for doing calibration, but it's not useful for doing any other kind of spoofing, at least not from what I've been doing. And so most of the time you're looking at, you're feeding the chip a sine wave, and you're trying to calibrate the chip to make sure that what the DAC gets back is an accurate sine wave. And so we put the chip in the debug mode, feed it a constant sine wave, pull out 4K of sample data at a time, and actually make sure that the chip is doing its thing. Now I'm going to cover a couple of things that people keep asking me about doing and why it's a good idea and why it's not a good idea. And the most common question I get asked is, how the fuck do I break regulatory requirements? You know, I have this chip, it can do a lot more power, it's the regulatory requirements and the chip calibration limits me to transmitting to quite a few dB less than what the chip is apparently capable of doing. Why is this a problem? The main reason is you don't have the equipment. Who here has an actual, like, 6 gig spectrum analyzer and power meter? Anyone? Right. That's the minimum 30 grand entry fee to actually screwing with transmit power. Because if you don't have that, you don't know if your device is actually distorting when it transmits. So the first thing is that you've got to have the right equipment to actually measure this. The main reason is that people think about is the regulatory requirements. The two parts are, there's a maximum amount of power you can inject into a channel, and because Wi-Fi looks like that funny, like, spectrum, that has a defined mask when you look at it on a spectrum analyzer, you need to make sure you don't transmit power into an adjacent channel that's higher than a certain level. And the specs, the 802.11 and the regulatory specs typically say what the maximum amount of power you can inject in adjacent channels before your device is out of compliance. The other thing is that RF is really weird. And at 5 gig, RF is extremely weird. And one of the weird things is that trying to find components that'll stay linear over 1 gigahertz worth of 5 gig bandwidth is exceedingly hard to do. And trying to design an RF circuit that's linear over that requirement is exceedingly hard to do. So trying to make sure that your design has both 2 gig and 5 gig amplifiers that remain linear over the course of that entire bandwidth is actually hard. And what tends to happen when you look at the output distortion is it's not straight. It does this, or it does this, or it's wavy. And so as part of the card calibration, they'll actually pick the maximum transmit power that you can do per channel based on what the actual card, when you test it, gives you distortion-wise. They'll say anything more than this much power, this frequency drives the transmitters into some kind of nonlinear behavior. They have to drop the transmit power. The third thing is that transmitting on 3 antennas, like half a watt, is actually pretty power hungry. And most of the stuff that you're plugging into isn't designed for lots of periodic bursts of a couple of amps worth of power. And so the power that your slot can provide you is typically less than what you're using to transmit. And the power requirements change based on the channel and what kind of thing you're transmitting. And this is all the crap that gets looked at in the lab. So the power consumption varies quite a lot, and decoupling caps only work so well. And so when figuring out, can I overclock, the answer is maybe. Even inside regulatory, even if your card is doing 2 or 3 dB less than the regulatory requirements say, sure, that doesn't mean that the card can actually do it. So I highly recommend that you get loan some equipment. And the other thing is, all of the high-powered NICs I've seen, they'll actually have a 5-volt input on them, specifically coming from some external source that's not the USB or the PCIe slot. And so you know you have a real high-power NIC if it actually has some external source. If you plug it into a mini PCIe slot, the card says it can do half a watt, it's probably distorting. The next thing people ask me to do is, can I make it tune to like 6 gig or 4.8 gig, or like, can I pick a tuning that isn't the channels to tune on? And the short answer is sure. The long answer is we only calibrated the NICs for specific channels for all the reasons I just talked about. And yeah, you can pick arbitrary frequencies to tune the chips to, but not only has it not been tested and you may damage things, the RF synth, RF is weird, and as you change the RF synth, it's doing digital, like, there's a PLL and it's doing digital upscaling, and it may generate noise spurs all over the place based on the current setting of the RF synth and what the divisors are and which bits you've turned on or off. So they actually test this stuff in the lab to say, okay, this particular synthesis setting for this particular Wi-Fi channel meets the requirements of low spurs and low distortion, and it's actually accurate. And you could tune it to arbitrary frequencies, but unless you test it, what you may actually be doing is damaging things. You may be actually generating more noise, and the thing may actually be drifting more than you'd like. So if you're going to fiddle with this for fun, get a spectrum analyzer and actually test this stuff. The next thing that people ask me is, how do I make my NIC work with the microwaves on, or how do I have it do a long-distance link? And all I'm going to tell you here is read the noise immunity code, because it actually twiddles all of the hardware inside the thing for tuning signal sensitivity. And so the NIC gets, a handful of microseconds during the preamble to lock onto the Wi-Fi signal and figure out the right signal size. If you're trying to do things like receive long-distance traffic and local traffic, which is quite high, the NIC doesn't have a lot of time to figure out what the right gain settings are. And so when I'm doing this stuff, and I know that I have a mix of long and far traffic, I'll have a NIC doing long-only traffic, and I'll have a NIC doing local-only traffic, so that I can have a higher percentage of being able to see faraway packets before the preamble stops and the packet starts and reception sucks. So if you're experimenting with noisy environments and long-distance weak signals, look at the ANI code and read the patent. I think this is the last thing on the playing around bits. So a couple of years ago when I was working there, we actually got the spectrum analysis stuff open source. So it's in BSD and it's in Linux. There are open source tools for pulling this stuff out. So all those pretty waterfall things you get from like the Ubiquity access points, when you put them into waterfall mode and you get a channel thing, all it's doing is it's putting the NIC into spectrum mode and scanning over all the channels. And so if you want to actually do it on an Atheros NIC without needing to have any other equipment, you can get a pretty good coarse-grained idea of what channels are busy, what channels are worth looking at, what's Wi-Fi and what's not Wi-Fi. And as I said, it's all open source. The thing to keep in mind is the same block doing FFT is used for RX and spectral mode, so you can't receive packets at the same time you're actually doing FFT investigations. When you trigger when you trigger a spectrum sample, it doesn't do receive for that period. So I'll use two NICs, and a lot of the enterprise hardware will actually put a second NIC in there, cheaper NIC, specifically to do spectrum analysis in order to pick the right channel to work on. And I don't think any of the open source access point products currently do this, but all the source code is there. If you want to play, then have a play. Now, I see a lot of people walking around with Atheros NICs hanging out of their laptops. And so I figured I'd talk a bit briefly about what's actually going on under the hood in these things. So all the HTC parts have a little Tensilica CPU that's sort of MIPSy, and a normal, bona fide, honest-to-God Atheros Wi-Fi chip in it. So all the crap I just talked about, you can do with the USB NICs. So yes, you can do spectrum analysis with the HTC NICs. Yes, you can vary transmit power. Yes, you can do all the fiddling with it. The first USB stuff had an actual separate CPU and PCIe NIC, the AR9280, and the one that I think everyone has is the single-band, single-antenna AR9271, which is slightly cut down, but it still does all the same stuff. You can still do spectrum analysis, not radar detection without 5 gig, all the same debug modes, all the same signal level stuff. So the driver in Linux mostly treats the USB widget as a dumb DMA pipe, and it knows a little bit about station stuff, so it can do frame retransmission in the NIC for doing TX aggregation and rate control, but we're trying to strip that out because the number one reason why you can't run more than 8 stations on one of those NICs in access point mode is because there's a limited amount of RAM on the NIC. But again, like the CPU can act as a dumb DMA pipe, and the plan is to do that, and then we can have as many stations as the driver allows you. And that's actually open source now. The firmware is open source. So if people are interested in doing things like running custom code inside the firmware on the USB NIC, you can actually do that. It uses the open source Tensilica GCC tools. I'll put the GitHub repo up here soon. You can build it, you can install it, you can fiddle with it. If people have questions about what kind of weird crap they want to do with their NICs, please let me know. I was going to do a walk through the HAL and show you guys how the thing holds together and what to look at, but unfortunately there have been some significant technical issues in getting things to work. So I'll finish by putting up where the source code is. And everyone takes photos. So Qualcomm Atheros actually put up a GitHub repo a couple of years ago that they're putting all of their projects inside. And everything except the cell phone software firmware and the 11AC firmware is currently up there, including firmware for their pre-11N USB NICs. I think it was a 5523, yeah. None of us have actually used it. Like, the hardware's out there and there's a driver for it. The firmware's out there. It's a normal Atheros device with a little MIPS CPU in there. So it's all documented. The only thing that I haven't opened up is Bluetooth, mobile, and 11AC. And the common question I then get at this point is, what the hell are we going to do about 11AC? Well, I don't work there, so I decided to sign the NDA to get source code access. So I have source code access, but it's not public. The source code isn't public, but you can, if you sign the NDA, you can get access to the firmware source, and it looks like an Atheros chip with a little CPU inside, as everything else does. The aim behind a bunch of us that are looking at this, and admittedly I haven't done very much, but I plan on stepping this up around September, is instead of there being, what we don't want to see is a lot of little individual companies publishing their own firmware blobs, and suddenly it's like, I have to use company A for station mode, and company B for access point mode, and company C for mesh mode, and then like there's a dozen different firmware blobs and a dozen different versions of the Linux driver to support things. Our plan is to have one tree that we all share internally inside the little NDA-enabled group and ship one binary firmware image so that we're not duplicating effort. The 11AC hardware is actually pretty cool. So if people here are interested in doing 11AC product development, the hardware will do meshing if you want to spend some time doing it. The hardware will do all the other stuff that you guys are used to. Please contact me and I'll bump you over to the Qualcomm Atheros open source group, and you can sign an NDA and have a chat with them. So the NDA program, I get a lot of cool hardware, mostly because I port FreeBSD to it for fun. There's an open source NDA program where you get access to their internal reference drivers, and if you're really nice and not jerk faces, they'll give you datasheet access, and you can talk to the developers, but they're all pretty busy people, so I don't recommend shouting them too many questions. If you can talk to the other people like me who have NDA access, we're quite happy to solve problems that take time that would normally take time away from the hardware developers. If you're really, really nice, then they'll actually give you reference design boards. So they actually want to see, there's a group inside of QCA that actually wants to see more open source stuff. They have a pretty heavy OpenWRT group inside of there, bringing their stuff up with OpenWRT and pushing things upstream. So if anyone here is actually looking at doing new product development and thinking of Atheros stuff, the place to start is by talking to these peeps, getting a good relation with them. They're down in San Jose near the San Jose airport, so it's worthwhile having lunch with them and actually talking about the sort of stuff you're doing and they're doing. And then lawyers are actually kind of cool. All the lawyers inside of Atheros that I worked with and still do here and there, they're the ones that got us access to all of this. They're the ones that approved all of this firmware access and source code access. So they're pretty clued in about open source and working with the community. So if you'd like to join, let me know. You can find me on the internet. It's not that hard. And we'll set stuff up inside of QCA for you to talk to them about stuff. I am trying to get together a group of people to actually do open source Wi-Fi development stuff in the Bay Area, because there seems to be a lot of interest, but lots of little disparate groups, groping around in the dark and not necessarily knowing what's going on. So if anyone is interested in coming to the Bay Area sometime later on this year and actually meeting some of the people involved in this and collaborating on like learning how the hardware works and what you can do with it and the open source drivers in Linux and other operating systems, let me know, and if there's enough interest, I'll finish putting it together. Any questions? It's either a good sign or a bad sign. We ran out of time. Cool. Well, the hardware is open, and it's a long cry from how it looked 15 years ago. Yes?
What advantage do you see is using the big parts to be custom accept that over software use?
Okay. So the reason why, if you're doing 802.11 stuff, this is good for doing data stuff because it's this big. And anyone who's tried doing actual 802.11 MIMO 11N decoding in SDR, your entry level is an actual FPGA board. Like the FPGA boards that we use, that I saw at Atheros, is like 2 of these sized FPGA boards running the Wi-Fi bit set quite a lot slower because they're FPGAs. So if you're trying to do like 20, 40, 80 megahertz 11AC stuff using an SDR, you're probably not going to be doing it at full speed, not with current hardware. The thing to keep in mind is, if you want to be doing a 20 megahertz channel, your SDR has to be sampling at least 40 and maybe more. And so, 11AC starts at 40 and goes up to 80. And then when you're doing 160 meg, suddenly you're going to have like 320 megahertz wide 320 megahertz wide stuff, and that's a lot of data. And that's then you have IQ, and you split that off, and you get 2 streams of data, and then you have IQ per radio chain, and that spirals off into hell, right? So for doing 802.11 sniffing, these chips are pretty good. If you're doing general signal analysis, these chips are not designed for doing general signal analysis. But they're like $2 on eBay, so yeah. Any other questions? Cool. Well, thanks.